Yeah. Yeah. Well, thanks everyone for coming. The idea is to have more of an informal group discussion. I will go through a few slides and look at the software, how we model these principles in the software, and then we'll have some time to discuss, which I think is the most valuable part of the session anyway. So I've been with eTool for 3 years now. I have an engineering background and doing business development, but I like the methodology, the technical aspect of it, and that's why I thought of putting a bit more into the technical aspect. Yeah, feel free if you want to grab a drink in the fridge. So first, before we get into the details, what I thought is just what is sustainable design? How can we actually define the performance of a building? What metrics are we using? And ultimately, how are we looking after the big picture? This is the big picture when we have to look at environmental performance, and the planet is only one. We don't have an intergalactic planet to borrow. If we start this one up and breaking it down from the nested dependency, in sustainability, we have the environment, which surrounding the society. Then we have the economy, which is just a mechanism for us as a social element. But ultimately, the environment is the most important one, as we all know. And this brings us to what environmental issues are we trying to fix or come up with solutions? What are the problems that is hurting the planet? And that's when it gets really, there's a gap here between the focus of what we need to address. So I put in there different environmental issues, from global warming to water stress, eutrophication, the use of non-renewable resources, land transformation, and included that line in there, which is what's the problem we're trying to fix. If we were trying to fix global warming, and global warming is caused by greenhouse gas emissions, we need to measure the performance of our buildings in carbon metric. We need to be able to identify the carbon performance of our buildings if we want to solve the global warming issue, which is the main environmental impact. So why? Because we are overshooting the carbon capacity of the planet. This map is emissions per person per year. Australia is around 20 tons per person per year, and the biocapacity of the planet is around 1 ton per person per year at 9 billion population. So we are at 20 tons per person per year. We have to drop it down to 1 ton per person per year. What we need to do, buildings represent a large portion of those impacts. So there's a huge opportunity for us here as designers, architects, builders to address that shift to a low carbon future. So we do have a carbon budget. We have to work with the budget that we have available. Out of that 1 ton budget that we have, in order to maintain balance, I broke it down into different end use or different activities. And buildings are here, so around 15% of our budget we can allocate to buildings. The rest is goods and services, food, transportation, and so if we are talking about 1 ton per person per year carbon emissions, and 15% is related to dwellings or buildings, we're talking about 150 kilograms per person per year. So it's just a way of setting metrics, numbers, so we can quantify performance. It's just a way of identify how green the buildings that we are designing are.
Apologies, I will interrupt from the question. Is it okay to ask?
Yeah, definitely. Yeah.
So how much does a percentage point equal in carbon emissions on average? saying 150 per 15%.
So this back to this graph is 1 ton is our budget per person. So breaking that 1 ton down into all the a personal carbon footprint, that's the 15% out of that 1 ton budget.
So from my perspective, I'm always focused on like 4% of that ton, or 4 kilograms effectively, is our carbon emission from waste.
Yeah. So yeah, the majority of the emissions coming from goods and services, food. It's the majority of our emissions, but the built form have a big. If you have goods and services, a lot of built form impacts associated with the factories, the industry generating the goods and services. So buildings, they are around 30% of the global emissions, and that's when it's a huge opportunity for us to reduce the buildings emissions and then help to lower the global emissions. So how do we know when we're designing green buildings? How do we know? We just went through an exercise here with Vince. He's developing a multi-residential development in Whitecomb Valley, and we were looking at numbers. How do we know how green is a green building? Is it going to be on the brown planet? Is it landing on the brown planet or the green planet? How do we define that? What metric we use? So I'll use a case study as an example, and this is a multi-residential project with Psaros, and that's will show us for each principle what we've done using the tool and the lifecycle design methodology to lower the carbon footprint for this development. First principle, we just use lifecycle design methodology. This is the only way you can truly tell how sustainable, what's the environmental performance of a building. You have to look at the life cycle impacts. So from materials extraction all the way through the end of life, from transport, assembly, use all throughout the whole building life, all the recurring impacts. They're all interrelated. So life cycle impacts and functionality. We have to maximize the primary function if we are designing residential buildings. There's no such a thing as a sustainable mansion. If we have all the sustainability features into a mansion, when we're looking at a per occupant basis, it's not going to have a good outcome. So we need to maximize the occupancy for residential development, or if it's a commercial development, the net lettable area, the primary function of the building. So functionality and life cycle impacts combined represent the methodology. So that's the primary, the first principle. Make it financially attractive. It has to be economically viable in order to be sustainable. So pick the initiatives that will have the best improvement on the environment per dollar spent. So sometimes we can focus or spend a lot of money on a certain area that is not giving you a direct benefit to the environment. So make sure you understand the improvement and list the priorities when deciding if you have a limited budget, where you're going to spend your money to get that improvement. For example, this is one representation. This is for the operational cost for the occupant. I would say this bar chart here represents around 50% savings for a 2-bedroom apartment that has a solar PV installed. So for this project with Psaros, they have a 2 kilowatt PV system for each 2-bedroom apartment, and now there are the energy efficiency features, energy monitoring, solar hot water. They drop the annual cost for the occupant by half. So 50% savings compared to average Australian dwelling. So it made sense financially for them to invest a bit more capital expenditure, but they have a payback, they have a resale value of that property, and the occupants will have operational savings throughout the
interesting to see there's more profit to be had from making windows replaces than two.
More, yeah. What happens is that the one bedroom has a smaller PV size. It was 1.5 kilowatt for the one bedroom. That's why they have a slightly lower savings.
That's
Yeah.
a profit margin, isn't it? You're paying the strata fee. The Psaros are making a profit, and what they don't have to pay for electricity, they charge a flat fee to everybody at the strata.
Yeah, what happens? They end up transferring that benefit to the occupant, so they will get the savings themselves. They will, depending on their profile of use, they will get the savings themselves. It's not managed by the strata. Each individual apartment has a microinverter, so they have their dedicated benefit for the PV. Yeah. It's not a one large system. Each individual they are able to build each individual dwelling separately using microinverters. Third principle is make it last. 90% of the houses are knocked down due to redevelopment, not because of their structural integrity, but because they're being redeveloped to higher density development. So they will buy, the price of the land will increase. They will knock it down, buy the surrounding house, and build a multi-residential development on that land. So what happens if you're building a detached house in Leaderville, for example, which is a high-density suburb? It's unlikely that it will last more than 40 years because the price of the land is going to increase so much that someone is going to grab that land and redevelop. So the houses are being redeveloped not because of their structural integrity. They're not falling apart because they're being redeveloped. So it's important to consider planning and density, build for the correct density, so they're not getting redeveloped for not getting knocked down for redevelopment. Future proofing, so it's unlikely that if it's a quality build, future proofed, unlikely that we will get redeveloped compared to the surrounding neighbor buildings. So it's all part of the quality of the design. Make sure that this building will last longer. And I put an example here for a building that lasts 54 years. The performance was 3.5 tons per occupant per year. If you extend that design life to 150 years, you get 10% savings on your carbon emissions per occupant per year, because you're spreading all the impacts with construction and materials over a long period of time, right? So put an example here with the tool. The idea is to show a little bit of the tool, a little bit of the presentation. So this is a version of this development. So it's an 80 unit development, the Psaros building. The current, if it's an NCC compliant building, if they're not doing anything else to the model, just getting it minimum compliant, it's the footprint per occupant per year. That's the unit of measurement. Is 3 tons per person. So that's the 150 years here, right? That's because it's a multi-residential development. It's going to last a long time. It's not going to get redeveloped. With 150 years. That's the structural integrity of that building. If it gets maintained, it will last 150 years. It's not going to get redeveloped. It can vary, I'm not sure what will happen to that region. This is on the Springs in Rivervale. Not sure. It's already a 5-story building, so I'm not sure where they go from there. If they're going to high rise, how dense that region is going to get. But structurally, there's no reason why it couldn't last 150 years if it's getting proper maintenance and all that.
That's put in consideration that you have to renovate, for example, bathrooms and obviously everything. That and new materials. Is that?
Yeah, exactly. So this is accounting for all the recurring impacts with maintenance, replacing your pipes when they need to, repainting, replacing your carpet, replacing your solar panels. So solar panels will last 25 years. every 25 years they need to be replaced. We need to account for all those embodied impacts, to make sure that it will increasing the design life, it will improve the overall performance.
Is there any consideration for taking for the occupants as they leave the building, in theory, transport emissions will drop over time as we run out of fossil fuels?
It's a good question. This is looking at the system boundary is for the building itself. It's not looking at the occupant transport impact. So this is defined by the location of the building. There's not much we can influence. You can have shared cars, yeah, but the occupant transport is not accounted on this boundary, system boundary. It's not part of this model. What we can do here, for example, is if we go into the software and then we change the design life, let's say, oh, it's not 150 years, we have a geothermal report, a geotechnical report. It's 54 years, which is the average lifespan for Australia dwelling. Surprisingly, it's only 54 years. So if we change this, if we change the life span to 54 years, then we get to that. So you increase the impacts because you're reducing that. So just to show you where we do this in the software. We go back to the next principle, which is make it functional. So still talking about functionality, but designing the houses that will maximize occupancy. This is now on a good trend. The houses are now reducing in size as we develop more multi-residential projects. The size of the dwellings are now reducing, so which is a good functionality outcome. So having in the past, for the past 20 years, the houses have grown 40%, and we have 10% less people living on them. Very poor functionality performance. But now there's a trend reducing the size of the dwellings and having more people living on them.
Just a quick question. If you separate housing and apartments, is the size of houses that we're building now compared to houses that we were building 10 years ago, is that actually decreasing, or is it only when you balance it apartments?
It's the average, yeah.
It is the average.
It's
so
the average.
The size of it, based on that, then could be assumed that the size of the actual building is still increasing.
Yeah. The size is increasing or maintaining the detached houses, but the overall average.
The average against the balance, yes.
Yeah, the benchmark.
The house's size is still growing.
Yeah.
In layman's terms, what I'm seeing in the market is larger buildings on smaller lots. Advantages are getting smaller, but the actual house is taking up all the garden space.
Yeah. So just not a good, if you want affordability, if you want a lower impact, just make it smaller. Very simple principle, and you can demonstrate that here with the occupancy. One of this project, Psaros, is so 90 units, 80 units, sorry, and it's a mix of 2-bedroom and 1-bedroom units. So a 2-bedroom unit will have an average 1.9 occupants. That's throughout the building life, and a 1-bedroom unit will have a 1.3 occupants. It's just an algorithm for calculating the average occupancy. It's hard to predict the occupancy profile, but for development with 105 bedrooms, you get 125 occupants. This is from here. It's 125 occupants, and 129 bedrooms, you get 139 occupants. So here we can see that just by increasing the occupancy, we get 7% savings. Because because we're spreading the impacts over a larger number of people. So all the construction impacts, the foundations, the materials, all the cranes, all that initial impacts, it's being spread over more people.
What's the split of singles and double bedrooms on that?
Sorry?
out of those 105 and 129, how many of them are single beds? And how many
I think it's half and half. Yeah, half and half. So they had a good mix. We were hoping that they had more 2-bedroom apartments, so therefore they would improve even further the occupancy. But it's their product they're selling. They have a market for the 1-bedroom too. So it's just demonstrated by increasing occupancy, we get carbon savings. We're not talking about energy. We're not talking about materials. We're just talking about functionality. So you can get that from in the model. It's where you select your. So at the moment it's 3,140. If you go here and change the occupancy, so let's say this is original design. It's 101. What was it? 105, and then 125 occupants. And all the modeling, it's all related to occupancy. All the formulas for energy use, it's all using this variable here. So when I change here, everything gets updated automatically. So we go from that 3,100 to 3,300.
How often do you update the formulas hidden behind the scenes?
It's up to the user. We have the templates. So when you go into the library, you have all the templates for the operational energy and the construction methods. You can have your own templates, but they often get checked when we have new construction methods, or when we have new efficiency, or when the building codes improve. That's when we recheck all the templates and all the assumptions. So this is, again, improving functionality, fourth principle. Then we get down to the more common stuff, which is looking at materials impact. Choose materials and construction methods that it's durable. You won't have recurring impacts. They have low embodied carbon. Timber is a good example. The life cycle timber in that picture. Low recurring impacts. So, for example, mineral paint is a good example. Mineral paint, it will last 25, 30 years. Instead of you having to repaint every 15 years, you're using a paint that will last longer. So reducing that recurring impact. Reduce transportation, so understanding where materials are coming from, what is the transportation mode, is it better to come from China by sea or come from Melbourne by truck? Not only the distance, but the transportation mode. And the ability to reuse. King's Square here is a good example. All the facades that they use on those commercial buildings, they were designed for disassembly. So one day, if those buildings get redeveloped, so somehow they can put it down, reuse all that facade somewhere else. So it was part of the design process, designing for reuse first and then recycle.
A lot of that transportation stuff, you not necessarily, you go to the showroom and buy X and you're not sure where it's come from, whether it's come from Italy by ship or from China by
or is it was made locally, or is it coming from Melbourne? So you can, when you look into the details of the product with the product manufacturer, you can track that down. You can contact.
But everything in the house, that's a lot of tracking down.
Yeah, we've done a lot of that work. So a lot of that is already on the templates. And what's happening now is product manufacturers, they are disclosing that information. As EPDs, environmental product declaration, and they state the from cradle to cradle. Their performance. So you can get that data. Some manufacturers, even more common now, we've probably seen this. They are showing the transparency, the whole chain of where their product's coming from. So, and when you go into the software, what's happening now is you, let's say we're looking at, internal finish, what I said before, and then wall tiles. This is for the wet area. We know the wall tiles. We know how much wall, the volume of the product. This is the product life. So we assumed average life of a wall tile to be 30 years. But if we get a data sheet from a wall tile that is 50-year warranty, we can change here. If the manufacturer is giving you a 50-year warranty on that tile, then you can compare different products with that information, and that's all gets fed into this party. So you define material life.
I mean, it's interesting because I'm guessing that people don't grow tired of the tile and probably rip it out after 20 years, regardless of warranty.
Yeah.
I mean, kitchens and bathrooms are the areas that like to be redone.
Renovated, yeah. Depending, they will do the grout, they will redo it, but can they reuse the tiles if the tiles are good quality? Yeah, so this will, if you have a recovery process for that tile, if that tile goes, yeah. So instead of that tile going to landfill and being impact, you get a little bit of credit for reinserting that tile into the primary loop for production. So this is
assuming it's being returned back into a like-for-like product.
No. So it will be, depending. Steel, for example, does, because 80% of the steel gets recycled as steel, but depending, this will probably get turned out to a sub-product used for something else. So a mix road base, or I don't know. So here's when you can get the product manufactured information and customize this field and customize your templates. Then you can compare if you're using this tile that is environmentally friendly versus a standard tile, what is the benefit it's giving you to your project. So this is.
So in relation to the 50 years of the building life, you're saying that tile will be replaced once?
So 150 years, this will be replaced.
Or 50 years?
Yeah, 5 times. Yeah.
Based on
It's going to land, but it's not being reprocessed and rebuilt. It's just shut down.
Yeah, exactly. Then you can associate.
Well, that's the other thing. You could then sort of arcs up a bit.
Yeah.
And I noticed they've got a distance transport.
Yeah, and then we have the transportation impacts. That's from product to site, and also from site to the disposal facility. You can customize all this if you have that information. So it gets into a very fine level of detail, but you can build all of those templates, and then that becomes really easy when you have that product. That product has that characteristic. You can just
you can assume that the bricks, doesn't matter whether you're buying it from offshore brickmakers or but you see are going to have similar properties.
Yeah, if you don't have an EPD to specify which product you're using, then you're just using industry average, which is. Yeah, it needs to be a certified EPD from an EPD regulator. They're really thorough with the audits they do. So we are getting more. You can now get into the tool allows you to import EPDs into the tool and customize products. So that's the idea, to promote those products that have EPDs. So that's the materials principle. Looking at that, when you optimize energy efficiency, the materials start becoming a big portion of the impacts. For example, with this multi-residential, they use bubble deck to reduce the amount of concrete, and also they get more span. So they're not only reducing the amount of concrete, but they're reducing the structural elements. So they're having less steel, less concrete, because they can have a longer span with the bubble deck slab. So it's changing the structural project. Yeah.
What's it called?
bubble deck.
Interesting product.
Yeah. They also used bamboo flooring, so they got rid of the carpet, but the carpet will have a high recurring impact every 10, 15 years. There's not many, well, it's improving, but the recyclability of carpet is low. So when you're using a renewable source product, you get that improvement. So it's just two examples here for life cycle materials. Sixth principle, making climate sensible. Aiming for high thermal performance is important, but make sure you're not compromising other elements. So the point here is we've done tests on, for example, double glazing and concrete slab. The amount of embodied energy that you're adding to your project with the extra, if it's suspended slab, if you're adding that thermal mass to your project to improve the thermal performance, the amount of embodied energy on the concrete itself is more than the amount of energy you save with air conditioning. You know what I mean? So you have to look at the trade-off. Are we really improving the overall carbon performance by adding more concrete or adding double glazing? Is it really saving that much carbon in operational energy? So you have to look at that trade-off and really quantify. For example, a 6-star house in Perth requires 70 megajoules per meter square. That's when you get 6 stars. If you're using more than 70 megajoules, you're not compliant. You need to be at least better than 70 megajoules per meter square. 70 megajoules per meter square for heating and cooling. So that's the amount of mechanical energy you need to maintain comfort, and that's the 6-star threshold, 70 megajoules per meter square of conditioned space. If you go to 8 stars, you reduce that demand to 34 megajoules per meter square. And then you throw that into the software, that gives you a 3% savings on your life cycle performance. So you're improving from 6 stars to 8 stars, and you're getting a 3% savings on life cycle performance. Because the 6 stars baseline, the reference, is you're not using that much energy anyways. So going from 6 to 8, there's a small return in terms of energy savings. You could, so the idea here with this principle is analyze the percentage improvement. So this is the dollar spent, and compare with other initiatives. So if you're spending another $2,000 to get the dwelling from 6 stars to 8 stars, what other areas could you spend those $2,000 and maybe get a 10% improvement on your carbon performance? Maybe you can improve your hot water system. Maybe you can improve your lighting. Maybe you can improve your energy monitoring, automation. Maybe you can add a bit more solar PV. Those initiatives will probably give you more environmental improvement than improving your star rate, improving your thermal performance.
Surprisingly, I think you feel about heating and cooling.
Yeah, there's a perception because the average performance of the current housing stock is around 2 to 3 stars, and that's a lot of energy going to heating and cooling. But with the minimum standard now being 6 stars, the house is already performing really well in terms of heating and cooling. So it's only 15% of your energy going to heating and cooling.
That extra expense.
Yeah, so you can change that when you are modeling. You can change that in your model by selecting the energy demand. So when we do the thermal performance reports, the calculations, we go in here, and then there's a field here that talks about the thermal demand. So it talks about the amount of megajoules for heating, cooling, and the amount of megajoules for heating. So so at the moment here we have for NCC version 3100. If we change that to the 34 megajoules, which I said, you go 25 here and 9 here. That gives you a really small change. So that's the 3% savings that I showed in here from 140 to 40. So you're saving 100 kilograms of carbon by improving your thermal performance. So that's the message here with this principle. Does that make sense? Yeah. Appliances and entertainment, big chunk is going here. Yeah, especially double-sided fridges, TV, standby, huge energy going to entertainment and appliances. So that's the trade-off. Sometimes you improve the thermal performance, and then you load your house with low efficiency appliances. You better spend that extra $2,000 on a high efficiency fridge, or
If you put it in the outside garage, it's going to be working twice as hard.
If you have the additional fridge, then it's not a good either. So don't spend all your time ensuring you've got a 10-star design and then blow it by filling up with inefficient and pointless appliances. This is the very focused on residential here, but this is applicable to commercial as well. Just looking at where you can get the biggest improvements in terms of dollars spent versus the environmental improvement. This is
I suppose this is where it gets difficult, because you've got to show the tenant or the resident how to manage that process to the conformance that you've designed to. Otherwise, they're not going to, new person moves in, they put that big monster fridge in the garage, under the direct sun.
It's coming. There's one of the principles is in regards to occupant behavior, and I'll talk about that. Renewable energy. So this is becoming a norm now. We see Australia is one of the biggest penetration for solar PV. We're seeing now larger scale projects with multi-residential developments. They're now fully covering the roof space with PV. Makes sense financially. Power prices are going up. Technology is developing. So this is just becoming a norm now for both solar thermal and solar electricity. And this is the aerial view of this development, the Psaros building. This is interesting because this is north here. So all the services that they had, this I don't know what this is, the lift, it was all designed so it was maximizing the availability for solar contribution. So they're minimizing shading, they're minimizing protrusions and gable roofs. They're just trying to design the roof really flat so you can install as much as you can. You maximize the generation capacity. So you can see this is fully covered with PV, every little space. So they could give every dwelling a 2 kilowatt system. It's really, really good outcome. The next principle is about the impacts that we're measuring. Low carbon is good, but not always low carbon means sustainable. We have to understand all the other impacts. For example, this photo is deforestation. If we are sourcing timber to build low embodied structure out of timber, we're solving the carbon issue, but then we're creating land transformation issue. So we need to understand all the impacts if we're not getting any poor trade-off. If we are adopting one strategy that is depleting the ozone layer, or if we are having a problem with land transformation or toxicity, So we have to look at the whole holistic approach, and we do that by running the radar charts. So when you run an assessment using life cycle design methodology, you have to report on different environmental indicators. As you know, Amanda, for the Green Star, you have to report on all those different indicators. And here is just by changing the impact indicator, you can look at the trade-off. So you can look at ozone depletion, for example, and you can now understand the impact on the ozone layer per occupant per year. So there's a metric here. You can look at all the other impacts and make sure you're not getting any. We get issues with land transformation with timber, and then we just have to make sure that timber is sourced from renewable sources. Just making sure we get this certificate from that timber that we're not having any different impacts other than carbon. So that's when we run those radar charts doing the modeling to identify any poor trade-off. The blue one is the benchmark, so the business as usual, and this is the proposed model. How much it's reducing on different indicators here. So we have global warming. This one is 20%, so 80% savings in terms of global warming. In terms of ozone depletion, it's 25% savings. In terms of eutrophication, so the depletion of natural water sources, this is 35%. Use of non-renewable resources, 25 or 75% savings. So we can make sure that this is very related to carbon. If you improve in the carbon performance, you will improve the other indicators as well. They have a good correlation, but sometimes you get those spikes, with land transformation or ozone, depending on the refrigerant you're using. So
This stuff here, though, it's all related to business as usual, which still doesn't address one of the first slides that you actually put up, which is where we actually have to get 20 times. Our business as usual is 20 times over where we need to be. Is that right?
yeah, that's a really good question. That's why percentage savings, if we say we're building a project that is 80% better than the benchmark, that doesn't really mean anything, because the benchmark is really bad. If we're improving against a bad reference, you still have a big chunk, a big portion of carbon emissions. So when you represent your results on absolute figures, instead of saying 80% better than the benchmark, I'm saying 0 carbon emissions per person per year, or 100 kilograms per person per year. That's how you make sure that it's a good representation. If you're just talking about savings compared against benchmark, it's not really.
The other way of actually putting this is still a percentage above where we need to be. We want to put it in positive.
Yeah. You want to reinforce the positive, but it's still, if you have a target which is the 1 ton, we are still 10% more, 20% more. It's the way you represent, but that's a really good point. Then the last principle is the human element. It's us, it's our behavior. There's no point of having a high efficient office or high efficient house if the way we operate. And there are ways for us to influence the occupant behavior in terms of design. So energy monitoring works really well. If you inform the occupant of the consumption, you can drive savings. So those behavior change programs, having that information on display so they can you get alarms on your phone if your weekly use was higher than last year. You can get comparative feedback, you can compare your energy use against the average for the apartment complex. can play that positive competition to drive behavior change. And then if you spec that automation during the design phase, you guarantee that will be implemented. So that can also be accounted as a credit for when you're modeling in your lifecycle design model. There's an example here. If we do include energy monitoring, let's get back to global warming here. There is a field here where we put an adjustment for, oh, here it is, it's already at 90. So we're saying that by implementing energy monitoring, you get 10% savings on your electricity use. You just drive the right behavior. So this is already with the energy monitoring savings, 2,900. If we go back here and we put it back to 100%, that means that you don't have any energy monitoring. You see that increase. So
do you ever do it any more?
Any
More than 10%?
we do. It depends on the level of automation. So we have we account for the model in the model is 3 levels of energy monitoring. One is the very basic one where you have your similar to this one. This is just metering the, so you have current clamps on your switchboard, and that feeds a web portal you can access on your dashboard. Or so actually this one is the second level. The basic one is when you have benchtop monitor. You kind of forget about it after the first week. The kids play with it and then they forget about it. This one actually can send you alerts on your phone and you can track online. So there's a next level of interaction. So that savings will increase depending on the level of interaction with the occupant. So you have the comparative feedback with the healthy competition. That's when we get to the 10% savings. That's maximum savings. So we look at research, what research is telling us in terms of the efficiency of this solution, and then we apply that to the model. So a 10% savings in electricity use will get a 7% savings in life cycle carbon emissions. So again, putting it into perspective, it's a low-cost solution giving you a 7% savings. So again, looking at the trade-off of where you're spending money, what improvement you're getting, you can look at all that. One thing I didn't show is the cost. So one of the indicators is cost. When I talked about making it financially attractive, the principle 2, that's when we look at cost. This is the cost per occupant per year. How much from construction to operation. So this is $1,000 to operate this dwelling per year. Gives you the breakdown of where you are spending majority of your dollars. Water heating, lighting, this is including car park lighting, common areas as well. That's why lighting is so big. Appliances, cooking, water pumping. This is just maintenance and construction for the hot water system. So it gives you some information about cost as well.
The other is so high, is that because it's got everything else in it?
Yeah, it's got everything else. So we list the 5 top ones and then we add them all into the other category. Then this is the last slide. Talking about the first big picture that I mentioned, the one planet that we have to look after. Make sure that we're achieving genuine sustainability. I'll show you the end result for this development. Because they were already into a lot of things, they already had centralized hot water system. They already had good functionality, you know, not very big apartments, good occupancy. Um, the starting point for this project was 2.5 tons, 2.5 tons per occupant per year. The benchmark in Australia is 4 tons. So what you're saying, if you're improving 50% against the benchmark, which is very significant improvement, you're still at 2 tons per person, which is very big. It's just blowing our budget with dwellings itself. So I agree with what you said there. You have to look at this figure, not only the savings. So they started well. They started around 50% better than the benchmark. And with all the recommendations running this through the design process, they managed to get it down to 900 kilograms. So it's a significant improvement, one of the biggest improvement for a development of this scale. That's why I really like this project. They really pushed the boundaries. You know, they invested some money on this. They tested different initiatives, and they managed to drop it down to 900 kilograms per occupant per year. So we're now seeing some large-scale projects with some good carbon performance. It's really exciting. So that's the conclusion for achieving genuine sustainability. I'm not sure if we have anybody online. We don't, so we're not going to get any questions from them. But yeah, this is it. If you know, I don't know if you've worked on similar projects. It's very hard when we ask for those figures. You know, what is the carbon performance? You know, how green is your green building? We often say, oh, it's 10 stars. It's eco. It's green. But how green is it? You know, we have to look at these figures here. We have to understand the impact per occupant or impact per meter square to truly understand how sustainable they are. So,
what is the impact per metre square net lettable area or net occupied area as compared to the population?
Yeah, you can change. So this is 900 kilograms per occupant per year. You can change your functional unit. Let's say we change into meter square of gross floor area. Yeah. For commercial, yes. For residential, we always push the occupancy because we always try to maximize the occupancy functionality.
So if we have 1,000 kilograms being our budget per person, what's our budget per meter?
Yeah, so the budget per person is 1,000 kilograms for everything. Out of that 1 ton, 15% is our dwellings, so it's 150 kilograms per occupant per year. So it's that 900 kilograms is good, but it's still not enough. We have to drop it down to 150.
We've done the conversion. What's it going to show us per meter?
So per meter square is 11 kilograms per meter square.
So that's below 1,000. It's a direct comparison. If you said 900 to 11, the ratio.
Yeah, I don't have that figure in terms of meter square because it depends. I have that figure on a per occupant basis because that first slide about the footprint is a personal footprint per occupant. This one here. This one. So this is per person. That's why I have the 15% for dwellings, but I don't know how much. Yeah. If we look at average dwelling size is 200 meters square.
But we couldn't do it just by Australia because this is a global tool, isn't it?
Yeah, this is global. Yeah. Ultimately, you know, when we're looking at per meter square, we have to get it down to 0. That's the ultimate goal. You know, design 0 carbon buildings. That's the ultimate goal for eTool and I guess for all of us as designers, builders, engineers, architects is make sure that that building is contributing to the environment, not impacting. So we're getting there. It's good stories, some challenges, but as long as we put numbers to things, we really understand, if we are getting there, we're in the dark. If we're not putting numbers down and analyzing the performance, we don't really know. So that's the main message with this.
Do you feel that in increase in the multi-residential sector that or that the importance of sustainable design? Because one of the biggest issues I see is if the developer has to pay upfront for these or has to charge that to the occupants, right, in selling those apartments, so like on comparing, as an occupant comparing the market, if the market isn't driven or looking for sustainable design, you might end up as a developer with these extras, but you don't find the occupants who are willing to pay for that because they might go and into development of cheaper apartments.
Yeah.
So do you
Definitely yes. Yes, definitely yes. Developer, they're here to make money. It turns out to be a good product, a good quality product, and that is sustainable. The sustainability is a point of difference. They still make money out of it. There's a market demand for it. Vince can share some of his experience as a developer, but we're seeing more and more of this from different motivations. So one of them is a marketing advantage. So you do this, for example, Psaros, because they see that this will create a marketing edge for them, a point of difference. When a consumer client is opting between two apartments, they will pick this one because this one is environmental friendly. There is a market demand for that as a sales and marketing motivation. It's not always a cost increase for the developer. They're finding ways, creative ways to deal with that. Some of them, they will lease the PV to a company, and that company will sell the power to the occupants. Some of them, they will sell as a green package. So they'll bundle the PV plus the energy monitoring plus the LED light and then sell as a package.
So
they will pay a premium for it. So the occupant, the future client will decide if they want that green package or not, and the uptake is about 60%. When they first did this, the uptake was about 60%, and they're like, forget about it, every building will now have this. So they test the market first, and then they saw there was a demand, and now they're business as usual practice for them. So that's the marketing and sales motivation. The other one is regulatory approvals. Councils are now finding ways to promote or give incentives for excellence, design excellence. So if you're a developer and you're willing to get extra story, higher density or higher plot ratio, you have to demonstrate design excellence. So instead of being limited with 4 story or 3 stories, you can get extra story, extra 8 apartments. That's a lot of yield for a developer to go to design it sustainably. So they're doing that and they're making money out of it because they're getting more apartments. Now they get more sales out of that development, and they are delivering good buildings. So there's a local council building regulation, building approvals, motivation as well. There's all sorts of different things happening, creative ways, to make it happen. But definitely, the other one is resale value, what I didn't mention. But if you're designing buildings now, they're not future-proofed with this stuff. In 10 years from now, if you want to resell your apartment, you're going to get stuck or if you want to resell your house, you're going to get stuck, because this is becoming more and more common. Everybody will have it. If you left it behind, you're going to lose resale value. So all of that, adds to the process.
I once had a cheap buyer was in the UK and in Canberra. To actually sell, you have to have an energy audit to prove how much you spend on your heating and cooling. It's part of the sale package. So it's a bar, a measure that we measure against. And he said, I've got the survey that was done from a house that went to market 2 years ago, same street, I use less energy than you do. Can you give me a discount on the price? Otherwise, I'm going to buy somewhere else. So the consumers are getting savvy about buying something that might have less operational costs.
Interesting.
I wish we did that here, actually.
Yeah, I wonder when it's going to happen around here.
5 10 years.
Yeah, we're a long way behind.
I'm being optimistic.
Have you got any experience in renovations? The examples you've shown here have been new from the ground up.
Yeah.
But from my perspective, 95% of the buildings